We're going to talk a little bit about the last little part of 12, which I did with the other part of the class the other day, and that is ethers, which is the last sort of organic group that there was in chapter 12. And again, this obviously will be on our exam. So when we last left sort of chapter 12, when we're all together, we were talking about, I think, phenols is where we sort of ended up. And remember that phenols are sulfur-containing groups. And we also talked, obviously, a lot in that chapter about alcohols, which are OH-containing groups. We talked about what happens with alcohols. Obviously, if we take a primary alcohol, and if we oxidize it, we do get our aldehyde group that forms. And as we talked about today and previously, if we oxidize it one more time, we will get our carboxylic acid that will form. And obviously, if we took a secondary alcohol and oxidized it, that will get us to our ketone, which is our 3-carbon run with the oxygen double bond in the middle. And again, remember, it will not oxidize there to carboxylic acid. That's where we talked about things like Benedict's test and Toland's test that you can use to sort of differentiate between those two. So what's left is sort of ethers here, and ethers have the functional group of carbon, oxygen, carbon. So that is basically the functional group of an ether. It contains a oxygen really between 2 carbon groups. It will have this sort of bent structure or V shape, very much like water, because if we do draw sort of our non-bonding electron pairs in there, that's basically 4 electron pairs around the oxygen and 2 bonds, which gives us that geometry of really bent or V-shaped. And this is sort of how we oftentimes will draw it in sort of line structure. There obviously are carbons on the other side of it and our oxygen coming into it. Now, in terms of how we're going to name ethers, there are a couple ways that you can name ethers, and we're going to go probably with the more common name of ethers, which is pretty good. When you go to sort of commonly name ethers, you pretty much can think of the oxygen in the middle, and you look to the right and find the group that's there, which is a methyl group, and you look to the left and you find the group that's there, which is also a methyl group. And in this case, since there are 2 methyl groups in this ether, that is where we get this name that we see here, dimethyl ether. So the common way of naming a ether is to pretty much look at the oxygen and then look to the right, look to the left of the oxygen, and you name those sort of carbon guys as groups. You put them in alphabetical order, and then you just put ether at the end of the name. Is really the sort of common way of naming it. So if we had something like this, again, we would come here and we would go to the right, and that's a 1-carbon group, which is a methyl group. We would go to the left, which is a 2-carbon group, which is an ethyl group. And again, we would put it in alphabetical order, ethyl, methyl, and then just put ether at the end of it. Now, in terms of really the IUPAC way of naming, which we won't do pretty much in here, but just to show you sort of how you technically would name it, IUPAC way of naming is actually, we would take the smaller part there and we would drop the YL off of the name and add oxy to it. And that would be methoxy. Longest carbon chain would be named just like an alkane. And this would be methoxy ethane is the IUPAC way of naming. Obviously here we'll just do more of the group way of naming, common way, but that's basically how you would go about naming it. If it was a IUPAC way, this would be something like methoxymethane as opposed to dimethyl ether. So here again, looking at the oxygen in our ether group, to the right, we have a 3-carbon group with a propyl group, 1-carbon group to the left, again, alphabetical methyl propyl ether. And once again here, this would be something like methoxy for the methyl group, propane. Again, if we did an IUPAC, but we will stick with the more common way of naming it. Any questions on that there? So let's take a look at some. Let's say we had that guy. Let's have and this guy. So why don't you name each of those there? All right, let's take a look at these here, which I think ended up being the same. Let's see how he did. So we'll come here. Really just download it. I know. That's all right. Don't do that. All right. All right. So let's take a look at these here, which I think I ended up with the same, but all right. So we'll go to our oxygen in these ethers, and here we have 1 and 2, which is an ethyl group. Going the other way, we have 1, 2, 3, and 4, which is a butyl group. Again, alphabetical here, butyl, ethyl, and an ether at the end. Now, if we do it on this one here, probably why I look familiar, 1 and 2 is an ethyl group. As a 1, 2, 3, 4, which is a butyl group. I'm gonna go with the same name on both of those guys. In that case, that happens, I suppose. Any questions on that there? All right. That was not so great. So ethers are used as anesthetics. They basically put you to sleep. Over the years, they have sort of replaced a lot of the regular ethers, and they've actually replaced it with some halogens. Less flammable, which is good. Also, a little less side effects and stuff like that. So these are really sort of ether derivatives. Again, we still have our ether sort of group right there in each of these cases, if we look at it. All right, so why don't you draw these structures here? This would be good practice, I suppose. Why don't we add, let's try a different one here. Let's do methyl propyl ether. And 4-chloral to hexanol. Okay, let's take a look here. So we'll start with this one. So remember, the name does give us a hint. So OLL is an alcohol. So pentane is 5. So we'll start with our 5 here. The 3 means that is where the OH group is located. And since you're drawing, you go left to right or right to left. And in this case, it really doesn't matter. They're both going to end up right there, no matter which way you go. And that pretty much takes care of everything there. And we'll do our hydrogens here. Oops, 2 and 3 there. Any questions on that one there? Ethanol, once again, OL tells us it's an alcohol. Ethane tells us it's 2 carbons, and really it doesn't really matter where you put it there. And that guy then would need 2, and that would need 3 in that case. Or you could draw the OH to the right of that as well, so it should be fine. This is our ether, and kind of like what we were talking about with our ester earlier today. When you go to draw ethers, since it's basically carbon, oxygen, carbon, you might as well just start with the oxygen in the middle and then really build your groups to either side of the oxygen. So because it's an ether, I'm just going to start with the oxygen. And diethyl means basically we have an ethyl group on each side, and ethyl is 2 carbons. So we're just going to put 2 carbons on each side. And then the rest is going to be our hydrogens at this point to get to 4. And then we're good to go. So kind of similar to what we were talking about with esters, with ethers, start with the oxygen, just kind of build out the groups on either side of it, and you'll be in good shape. That then would be what we would do up here for our methyl propyl ether. So once again, going to start with the oxygen. Propyl, and it doesn't matter which side you put it on since you're drawing it. So that's 3 carbons. So I'll just go 3 carbons this way. And methyl is 1 carbon, which would go this way. And once again, here we'll just put in our hydrogens to get to 4, and we should be in business, I think, at that point. Any questions on that one there? And lastly, here we have an OL, which is an alcohol. So hexane there is a lot. So we'll go down here, perhaps 1, 2, 3, 4, 5, and 6. 2-hexanol means the OH group is on carbon number 2. So I'm actually going to go left to right here and call that carbon number 2. Since I chose that as carbon number 2, that means that for me, carbon number 4 would be right there. And then at that point, everything else here will be hydrogens. And R3. Any questions on drawing any of these guys here? Yeah. Yeah, so if you drew it like this, which I think is what you're asking, it's all good. Yeah, either way. Yep. Other questions? Yeah, so the nice thing about when you're drawing it is you really could kind of choose whichever kind of way you want to go. So as long as you sort of have the correct number of carbons on either side of the oxygen, for example, it's okay no matter which way you go. It's basically just the same molecule, just turned around. Other questions? Okay. All right, so to kind of finish up some of the stuff we talked about here in this chapter, we obviously talked about alcohols. To finish up on some of the properties of alcohols, alcohols which do have that OH group, which is a polar group, partially negative, partially positive. It is able to really hydrogen bond with itself, which obviously would be another alcohol. And it's able to hydrogen bond through the negative side of one to the positive side of the other. And this is what is referred to as hydrogen bonding. And hydrogen bonding, it is really a strong intermolecular force. And an intermolecular force is basically the force that holds one molecule together with another. And all intermolecular forces are really just a basic idea of the positive side of one molecule is attracted to the negative side of the other. So the opposites attract. And that's basically what holds one molecule together with another. That could be the same molecule with itself. So like the same alcohol with the same alcohol, how it stays together. Could be like an alcohol and some other guy coming together, how they interact with each other. And in terms of intermolecular forces, there's 3 types. There's hydrogen bonding, which is the strongest type of intermolecular force. And hydrogen bonding is a bond between hydrogen and nitrogen, oxygen, or fluorine. So in order for somebody to be able to hydrogen bond you have to have a hydrogen that's directly attached to a nitrogen, oxygen, or fluorine. And if you look on the periodic table, nitrogen, oxygen, and fluorine are the most electronegative elements, which means you're going to get a really polar bond in that case. You're going to get that separation of charge where the hydrogen is going to be more positive, and either the nitrogen, oxygen, or fluorine is going to be more negative. So it creates a really polar type bond. And these are typically what happens with things that are polar molecules that have the basically ability to hydrogen bond. So things that have that sort of bond in it. Now, there's also dipole interaction, and that is an intermolecular force that polar molecules use. And those are polar molecules that do not have the ability to hydrogen bond. So they're still polar, which means there's a positive side and a negative side, just like we talked about when we talked about bonding. There's a positive side of the molecule, negative side of the molecule, which is attracted to positive side, negative side. It's pretty much this interaction up here. Positive side of one polar molecule is attracted to another one. It is still a relatively strong sort of interaction, but not as strong as hydrogen bonding, but dipole is a relatively strong one. And that is usually the strongest force that's used between a polar molecule and another polar molecule, or a polar molecule in itself, which is obviously another polar molecule together. The weakest of all intermolecular forces is what is referred to as dispersion forces. And these are the ones that nonpolar molecules basically use. And nonpolar molecules, if you remember from bonding, are really molecules that, as a whole, basically are sharing electrons equally. So the electrons are equally sort of distributed over the entire molecule. And what that essentially means is typically a nonpolar molecule has like no charge. There's not like a positive side or a negative side because electrons are equally being distributed over it. So how nonpolar guys basically are able to interact with nonpolar guys and other things is they use dispersion forces. And what dispersion forces are temporary sort of attractive forces that occur. And how that could sort of happen is, for example, if you had a nonpolar sort of molecule and it's sort of neutral, there's no positive side or negative side. What could happen is all the electrons could decide to kind of go to the left-hand side of the molecule because they're flying around. They all could just find themselves kind of over there on the left-hand side of the molecule. And what ends up happening is that will temporarily create in a nonpolar molecule, a molecule that now temporarily has a side that's more negative and a side that's more positive, which it normally doesn't have because those electrons kind of went one way or the other. And what that's able to do is, if it happens to be next to another nonpolar molecule, it will also create a temporary sort of charge in that guy. Now, these two sort of nonpolar molecules that normally don't have any type of charge temporarily gain these charges, and now they have a way to interact with each other. And they're weak and temporary because as soon as those electrons go back, they're going to kind of break apart. They're not going to be able to maintain those interactions with one another, and they're going to basically break apart. This is also why things that are, say, polar and non-polar, when you put them together, they really don't mix, because things that are polar are going to try to use hydrogen bonding or dipole interaction, while things that are non-polar are using these very weak temporary forces, which means when they get together, only for a very short period of time are they able to interact well with one another. It's like oil and vinegar salad dressing. You can mix it up, right? And it will mix, but eventually what will happen is it'll all separate out. And that's because oil is non-polar, vinegar is polar. So for a short period of time, they're able to kind of keep that interaction. But if you look at your salad dressing at some point, right, everybody's going to kind of separate out from one another because they have no way to maintain those interactions. So these intermolecular forces are really important in terms of when we talk about things that are in our, say, organic chemistry, and things like boiling points and melting points, and sort of the effect of whether or not it would be sort of a high boiling point or low boiling point. So for example, if we take something like an alcohol that has the ability to hydrogen bond, as I mentioned earlier, with each other through the negative side and positive side, That is a relatively strong bond, that hydrogen bonding. And because that's a really strong interaction, it's going to take a lot more energy to separate out the alcohols from each other. And that is what normally happens at the boiling point. Something goes from liquid to the gas phase, right? And as you go from liquid to gas, they completely break apart from each other to get into the gas phase. So because the alcohols, for example, are held together by these really strong hydrogen bonding forces, it takes a lot more energy to break them apart. The result of that is a much higher boiling point and even a melting point. Then we see something like just an alkane, which is just carbons and hydrogens, right? And alkanes are nonpolar. These guys are nonpolar, which means they're going to use dispersion forces. And because something that's like an alkane is only going to be able to interact with another alkane through dispersion forces, these really temporary, weak type of interactions, it doesn't take a lot of convincing to get that alkane to go into a gas phase. And that's why if you think about sort of the early alkanes like methane, propane, butane, they're all gases under normal conditions. And a lot of hydrocarbons are gases because frankly, they're held together by very weak interactions between them, which means you just sneeze at them and they're able to basically break apart and go into the gas phase. It doesn't take a lot of effort, as opposed to something like an alcohol that can sort of hydrogen bond, which is going to keep themselves together a lot longer, more energy to break them apart. Now, for the most part, things like alkanes, these kind of carbon guys are going to have very low melting points and boiling points, as opposed to an alcohol, which would have a much higher boiling point or melting point. And in between, we have our other guys. We have our ethers, we have our aldehydes, we have our ketones. And again, the aldehyde and ketone have that carbonyl group, which helps it sort of stay together, but they can't hydrogen bond with themselves. So they have a much lower boiling point than an alcohol. It's only to what we talked about today that there is actually something that can beat the alcohol, which is the carboxylic acid. And again, the carboxylic acid actually has the highest boiling point and melting point because it has that group there that we talked about, which is two polar groups sitting there. And what happens is when two carboxylic acids get together, that's the same carboxylic acid, basically it's able to bond like so. And we'll do our positive, negative, negative, positive. And we'll do our oxygen like that. We'll go like this. So what happens here is you get some bonding here, and we also get some bonding here, and it's able to do basically two hydrogen bondings with itself, which makes it even strongerly held together and takes a lot more energy to actually break it apart. So something like carboxylic acid, because it has those two kind of polar groups, will able to participate with hydrogen bonding with itself and hold itself together a lot stronger than even an alcohol. So it's one of the few things that actually will have a higher boiling point and melting point than, say, an alcohol. Alcohols could pretty much beat almost all other organic groups, but the carboxylic acid actually could beat the alcohol in terms of that because of that hydrogen bonding. So the moral of the story in terms of bonding, boiling points and melting points is if something has the ability to hydrogen bond, it's going to have a relatively good boiling point. If it can't hydrogen bond and it's just carbons and hydrogens, it's going to use dispersion forces, which are really weak and should have a much weaker or lower boiling point and melting point. Now, if you happen to be comparing two things that do use dispersion forces, and that's the only thing they use, so two different types of, say, alkanes, for example, the one that is larger, has more atoms, would actually have the higher boiling point than the other alkane. And that's because larger alkanes have more atoms. More atoms means more electrons. More electrons means a greater chance that they will move around, and you can get that kind of dispersion force sort of happening. So in comparison to two things that have dispersion forces, the guy with the larger molar mass is typically will have the higher boiling point because it has more electrons than the guy that has the smaller molar mass. Again, comparing two things that have pretty weak forces, dispersion forces and stuff like that. Any question on boiling points, melting points? We obviously classified our alcohols, I think a number of times last time, but since we're on this slide, remember that when you're classifying alcohols, we look at the carbon that has the OH, and it is how many carbons are directly attached to that carbon. So that is a primary alcohol. This is the carbons attached to two other carbons, which would be a secondary alcohol. This carbon is attached to three other carbons. And then we always look at the carbon that's directly attached to the OH group, and then how many carbons are directly attached to that in terms of the primary, secondary, or tertiary. So here, if we looked at this guy here, we would look at this carbon. It is directly attached to that carbon and that carbon, which means this should be a secondary alcohol. This is the carbon that's directly attached to the OH group and is directly attached only to that carbon, which means this would be a primary. This is the carbon that is attached to the OH group and it is attached to one carbon there, two carbons there, and three carbons there, which would be our primary, our tertiary alcohol in that case. And as we talked about, if we oxidize this guy, we get an aldehyde. We oxidize this guy, we get a ketone. And if we oxidize this guy, we get nothing. And that's because this guy has no hydrogen sitting there. So that prevents it from going through oxidation, which is necessary, obviously, for the other two to go through it. It's those two hydrogens that's necessary. Any questions on that there? Now, we talked about boiling points. We also talked about solubility in water, which also basically revolves around hydrogen bonding. So once again, pretty much alcohols have the exact same bond that we find in water, which again makes it very soluble in water because again, it has the ability of the hydrogen bond. Much like all the other organic stuff that we talked about, pretty much solubility will start to decrease as you build out a lot more carbons and hydrogens. There'll be less of those OH groups. So it would be something that would be insoluble in water. So as you can see here, this is all non-polar, the part in the box. And even though it still has this polar group here, pretty much this guy gets in the way. So it's just in the way of it being able to interact well with water. And as we talked about earlier as well, or a number of times, basically in order for water and things to dissolve in it, you have to break apart the water-water interactions and replace them with very similar interactions. And they have to be kind of similar size. So things that are really large are not going to basically get in there well, and they're going to try to use dispersion forces. Again, something relatively small will be okay in that particular case and be pretty soluble. So usually around that sort of 4-ish mark in terms of alcohols, you start to run into some trouble in terms of solubility. Before that, things are relatively pretty soluble because they're small. They have that OH group, but again, as you build out that sort of non-polar side, you do run into some trouble in terms of solubility. Hand sanitizers. Lastly, phenols, which I think we also talked about, are really alcohols that have the benzene ring on it. And that's, again, sort of that historical name. And these guys are slightly soluble in water, really because of the benzene ring. It's kind of big and bulky a little bit, so it does sort of get in the way a little bit of it being soluble in water. But it's able to kind of do a little proton donation there to our water here and make that sort of guy, that this sort of ion that comes off of it as well. All right, so just looking at these here, this guy here, would it be soluble in water or insoluble in water? This guy would probably be insoluble in water. Too many carbons here. So again, upwards of 3 or 4, you're gonna kind of be okay, really up to 3, but at 4 or more carbons gets in the way, going to be insoluble here. This here will be soluble, again, less than 3 carbons. So it's going to be able to hydrogen bond okay with water and be able to interact well as opposed to the top guy there that will have stuff that gets in its way. Any questions? What's that? For alcohols, it's pretty much up to 3, you're good, carbons. But at 4, you start getting into that kind of slightly soluble, which, as I mentioned earlier today as well, slightly soluble really doesn't a lot of times kind of lean more towards it being insoluble. So it's really not very soluble at that point. So alcohol is about 3-ish or so, you're okay. Carboxylic acids, as we saw today, you could get up to about 5 or so, you'll be okay. But usually most of those things that have some type of polar group, that kind of 4-ish range or 5, is really where you start to see sort of solubility start to drop. Again, slightly soluble does mean that a little bit of it will dissolve and kind of mix, but a good majority of it really won't mix really well. So again, slightly soluble, really more so of it being insoluble as opposed to something that's just straight up soluble and mix. Other questions? All right, I think that will wrap up chapter 12, I think.